Hello, everyone. My name is Shantanu Paul, and I am a research fellow at the Trusted Network Lab at QUT. So in Trusted Network Labs, we conduct a monthly seminar series called BiTS, Blockchain and Internet of Things, by inviting speakers from academia and industry. Today, we are delighted to have Professor Bhaskar Krishnamachari from University of Southern California, USA. Professor Krishnamachari will be talking about blockchain technology and its application to the Internet of Things. And after the presentation, we will upload the talk recording on our Trusted Network Lab website and also make it available on YouTube. Professor Krishnamachari is the director of the Center for Cyber Physical Systems and the Internet of Things at USC School of Engineering. His research spans the design and evaluation of algorithms and protocols for wireless networks, distributed systems, and the Internet of Things. He is the co-author of more than 300 technical papers and 3 books that have been collectively cited more than 30,000 times. He has been received the Best Paper Awards at IPSN 2004 and 2010, Mobicom 2010, and VNC 2021. He is the recipient of the NSF Career Award, the ASE Tarman Award, and has been listed in MIT Technology Review's TR35 and Popular Science Magazine's Brilliant 10. So once again, we welcome Professor Krishnamachari for today's talk. And Professor Krishnamachari, over to you. Thank you.
Thank you, Shantanu. It's really a pleasure to be here and to give this talk. And definitely sounds like my talk is right along the lines of the topic of the whole series, looking at blockchain technology and IoT and that intersection between them. So I'd like to begin by just kind of motivating why blockchain is an interesting academic research subject. And this is a question I actually get asked a lot by colleagues and by others who are working in other fields. They hear about blockchain often in the context of Bitcoin, cryptocurrencies, Coinbase, and the part of it that they're focused on in terms of what they hear from the news is only about cryptocurrencies and trading. And I think there's some interesting questions there. In fact, we also look at those questions in our research. But I also think it's opening up a whole new dimension in computer science and computer engineering that should give us all reason to look deeper. So and I think the dimension it's really opening up is what I would call decentralized systems, and I believe they're actually different from, and I would argue they're different from, traditional distributed computing in some very key respects. And because of this new domain of decentralized systems, we're going to need, and I'll talk a little bit more about what I mean by decentralized systems, we're going to need more transparency and trust guarantees that blockchain technology is kind of providing and is holding the promise to provide. And so with these decentralized systems, with more transparency and trust, it's really enabling, I claim, completely new types of and combinations of value transfer and information transfer, and combinations of value and information transfer that typically, traditionally, were decoupled from each other and relatively done more inefficiently. So it's improving efficiencies, it's creating new capabilities. From a research perspective, we then have the opportunity to improve efficiency and scalability. We have the opportunity to look at questions of, what are some new applications for this technology? Where is it useful? Building out, prototype demonstrations of this technology in use in those applications. And for researchers that are more algorithmically inclined, there are algorithms problems at every layer, starting from smart contracts to, starting from consensus layers to smart contracts and in the applications themselves. And from a research perspective, the value that we can add as academic researchers is, in a field that has been almost in the last, I would say, decade or more, really been primarily the domain of industry and kind of, people deploying solutions out there and new protocols, where academic researchers can add values to take those practical solutions that are out there and kind of look at them with a little bit more of a critical perspective, helping to verify that these things actually satisfy the claims that are made about them in marketing, but also systematizing what is out there. So you might see, a point solution and some other competing solution out there. And then as a researcher, you can look at those solutions and identify some underlying problem that they may have parameterized in the design space differently. And that lets you kind of take a step back and see a bigger picture from an academic perspective. That's one of the ways in which we can add value to the field. And this isn't new to blockchain technology. It's happened before in other domains. You can go back to something like the earliest aircraft, right? The first flying machines were built by people who essentially, the Wright brothers had a workshop, and they tested things out very empirically, and they built the first airplane. But to go from the Wright brothers flyers to the supersonic jets that we have today, it took a lot of engineering, a lot of academic work to understand the basic principles, how they applied, how to engineer, how to optimize these systems. And so there's a lot of academic value that got added to the early solutions, which were kind of developed more empirically, right? So nobody today in any major aircraft industry is trying to just wing it by trying new airplane designs, kind of hacking up a new scheme. They are really applying fundamental principles that have been learned through decades and decades of academic research. So I want to kind of us to keep that in mind, because it's a new field, because so much of the conversation is dominated by industry development. Sometimes people in academia have almost a pessimistic view of the value that academia could bring to such a domain. And I think it's quite the opposite. I think it's precisely domains like this that academia can actually contribute a lot. So with that being said, I talked about decentralized systems. This is a text I like to share often when talking about distributed systems. This is from sometime in the 90s. It was a collection of kind of drawbacks or shortcomings of distributed computing that were identified. And the statement that was made by Peter Deutsch was that one of the big fallacies of distributed computing is that there is one administrator for the entire distributed computing system. And in many cloud-based platforms, that's kind of true, but everyone eventually comes to recognize in the long run that the interesting applications are not always best served by systems that are centralized in this way, right? So, and there's a distinction there between distributed and decentralized, where distributed is referring to there being multiple computers. Centralized versus decentralized here is referring to who's administering them, right? Is your distributed system centralized? That would mean one administrator. Or is it decentralized, which would mean there are many administrators, right? It's this type of decentralized computing systems that blockchain really is helping to grow as a domain. So I would call decentralized systems as distributed data and communication and computation systems that allow for the management and movement of data across administrative boundaries, economic boundaries. And because the data is going to flow across these boundaries, we need to ensure privacy of the data, we need to ensure security, and we need to have certain notions of trust built into the system. And I do believe that this is the class of systems where blockchain is going to really contribute, right? And so we take IoT as our kind of application domain in this talk. Well, what is the Internet of Things? It's a collection of sensors and actuators and serving some application networks and computation happening. The question to ask is the same question in these two slides, right? It's a distributed system. There's clearly many different IoT devices in an IoT system. But are they all, first of all, distributed? Yes. But are they centralized? Is it the assumption, is the operating assumption of your system that there's only one administrator for the entire network, right? If not, if it's a sufficiently large scale application, the answer will be it is not. Then we need to think of it as a decentralized system. We're going to run into issues of security and trust and crossing economic boundaries. And so that's a place where blockchain is going to play a role. So I actually think blockchain and IoT really go hand in hand together. When you talk about large scale IoT systems, they're going to naturally cross administrative boundaries. Blockchain has a role to play there. I won't belabor the points in this slide. They're quite well known. Blockchain, really as a domain started when Satoshi Nakamoto's white paper was posted and Bitcoin was released. And since then, there have been a number of developments. I think a big milestone was the starting up of Ethereum as focusing more on not just the cryptocurrency application and the storing of data, but also to do decentralized computation on the chain using this notion of smart contracts. And then perhaps another milestone could be thinking about use cases of blockchain that are not just permissionless, but also in permission settings for industry consortia, such as the work by IBM and others on Hyperledger Fabric. And I would say there's been kind of in the last 5 years, given even these early versions of blockchain, I would argue even today, they're not that great. There's still a lot of engineering work to be done to improve their functionality and performance. But even with those capabilities that are emerging, there's been a lot of innovation in the applications, right? And of course, a lot of the early applications have been in the world of finance, decentralized finance, but there are applications, again, that are maybe waiting in the wings or are starting to pick up in other domains, and IoT definitely would be one of them. So if you kind of want to see that evolution, one way to kind of picture it is to say we started out looking at decentralized currency with Bitcoin. Then people looked at, well, once we have these public immutable ledgers, we can store different types of transaction data on them that are not just about value transfer. But then with the capability of computation on chain, it's really giving us a decentralized computation platform to run applications that also benefit from that transparency and that security and immutability properties. And one of the interesting aspects of decentralized computation on blockchains is that these programs that run on a blockchain, smart contracts, can actually enable a credible implementation of a game theoretic mechanism. What I mean by that is everyone knows what that smart contract encodes. They know the conditions under which it'll be triggered. There is absolutely no concern that for some reason, some human actor will choose not to trigger them. In some sense, there is this guarantee that once that smart contract is out there on the chain, its behavior is fairly deterministic. And so you know what to expect when certain events happen. And so if you want to build in incentives and deterrent mechanisms into the smart contract protocol, into that application, they become kind of credible by virtue of the fact that it's transparent and immutable. So here's another kind of overview slide I'd give for people that are somewhat new to blockchain. What I call the kind of generalized blockchain stack, that at the really base layer at the bottom, we have a lot of cryptographic building blocks, everything from public key cryptography, hashing, Merkle trees, digital signatures, zero knowledge proofs, verifiable random functions, and others. Then above that, we have a layer of Sybil control mechanisms that are really techniques to ensure that it's not easy to fake having multiple identities on the platform and have a voice more than you deserve to have on the platform. And for permissionless systems like Bitcoin, of course, everyone knows about proof of work as kind of this very energy expensive, computation heavy approach to Sybil control. But there are alternatives, and proof of stake has emerged as a credible one in recent years. And the bigger, there's always an option to do permissioning when it comes to Sybil control, which is to say that every device allowed onto the network by some authority that's permissioning in these nodes. So on top of a Sybil control mechanism, you can have different types of consensus. Some people refer to proof of work as a consensus scheme. It's actually a Sybil control scheme that's going hand in hand, for example, in the case of Bitcoin, with the longest chain adoption scheme for the consensus mechanism. But there's a long literature in the Byzantine fault-tolerant distributed computing literature on consensus protocols, and they can be used in this domain. Above that is kind of a layer of how are you going to organize the data or information or transactions that are stored on chain? Will they be in the form of blocks? Are they going to be chained together linearly? Will they be timestamped? Is there going to be perhaps a different data structure like a directed acyclic graph, which only offers a partial ordering between transactions? Then a layer above that, what has really emerged more recently perhaps, is how do you scale these blockchain protocols, and whether it is through distributing them into what are called shards or by using state channels, which allow some amount of transactions to happen kind of in a side channel or offline and then be committed to on the main chain. Above that, we have a layer of actually putting in computation on the chain, often in the form of state machine replication, and then running programmable smart contracts on these kind of virtual decentralized computers. And then once you have that decentralized computer, you can build applications on top, and sky's the limit in terms of what applications one could come up with to run on a blockchain. So it's kind of helpful to kind of see that blockchain is these many different layers of things, even for a research perspective, to kind of then ask yourself, where do I want to focus? What is this particular topic I'm interested in? Which layer is really my focus of interest? Am I trying to contribute to fundamental building blocks, new Sybil control mechanisms, consensus mechanisms, or am I interested in the throughput scaling problem, or am I really interested in new types of applications, right? So just a very quick kind of 10,000 foot overview of research in my lab on blockchain since roughly 2017, 2018 or so. We work on a number of decentralized protocols, many in the context of IoT, and I'll talk about that today. We actually do have work on decentralized finance, which I mentioned is kind of the hot topic in this domain, including most recently some work on automated market makers, which show up a lot on cryptocurrency, decentralized exchanges, and so on. The other place where we found blockchain to be useful as an enabling tool is in the context of IoT data marketplaces, and I'll be talking about that as well today. And then kind of the last bucket of things where we've done some research is applying blockchain to networks and cybersecurity problems that show up in different network settings. So today I'm going to take 4 or 5, actually maybe 6, depending on how much time we have, case studies of research from my group over the last 5 years or so, and hopefully just kind of walk you through some of the flavor from a technical perspective of what is involved in working in this space. So the first part here, I'm going to talk about some IoT-friendly blockchain protocols or decentralized blockchain-based protocols for IoT. So the first case study is based on some work with my PhD student, Mehrdad Kiamari, where we were asking kind of this question: can we make mobile devices, and it could also be in fact IoT devices, they don't have to be mobile necessarily, but sort of wirelessly connected devices with some variation in their connectivity. How do we make them? Can we make them first-class citizens in a blockchain system, in particular when it comes to validating transactions and really participating in the consensus process around the validation of transactions? So one of the benefits of such a system, if we could answer this question in the affirmative, would be that we would have greater security and scalability, just because there are hundreds of millions, probably billions of mobile devices on the planet, right? Virtually every human has one, and I think the ratio is probably more than one device per human already on average in many parts of the world. So that in turn means that you have greater user adoption, and from a scalability perspective, if you have more nodes on a network, you can have more shards if you want to distribute, and that will help scalability in terms of performance. And then of course, there's this question of applicability to IoT. If the devices that were participating in consensus were not just mobile devices, they were actually even IoT devices, there could be even larger numbers of them, and are there places where that could be beneficial? So that's kind of a set of motivations for why we might want to consider this question. But of course, the challenge to be solved here, and the reason today's blockchain protocols don't really work with mobile devices as first-class citizens, is quite simply they're not very capable in many cases. And second, more importantly, perhaps, they are not always online, right? And your phones are subject to some extent to the availability of a network. They may be switched off at any arbitrary time. You go to sleep, you may turn off your phone's network connectivity, or if you're in airplane mode, or or if you just happen to be traveling out of town. So there's that kind of connectivity challenge, and potentially some issues on storage and computation as well. Our focus in this work is really more on that scalability and addressing the connectivity issue. So the work that we've done in this, it's called Blizzard, and there's a paper up on arXiv, there's a link to it here, that The dimension in which it's kind of improving on prior blockchain systems really is to do with this number of validators potentially going from hundreds of thousands of devices, if you want all online devices, to validators that are potentially in hundreds of millions. And of course, you're getting that because of the ability to handle mobile devices. So what's the idea? So we're actually building on top of an existing protocol called Avalanche, which uses gossip-based consensus. Roughly speaking, and I won't have time to get very deep into how Avalanche works, but roughly speaking, the idea there is that nodes, when they want to validate a transaction, query a random number of other nodes about their kind of view of whether this transaction is valid or not. Is it in the right ordering in the DAG structure that the data is organized as? And based on the responses that they get, they take kind of a vote across everyone that they talk to, and they use that to come to some conclusion of their own. And then when they get asked, or they can propagate this information to other nodes. And so there's this process of basically propagating the transactions information through a series of random gossips. Now, the thing about Avalanche is that it requires every node to be able to, at any time, arbitrarily pick a random node in the network to send a message to, right? Now, in a mobile network, imagine you have 100 million devices. They can't even store a list of the rest of the 100 million devices on the network to be able to identify one of them and send it a message. There's no kind of direct peer-to-peer contact between mobile devices. It's going to be trivial to implement. And so you're going to need some combination of online brokers and these mobile devices. So there's sort of a two-tier system that we propose, where there are brokers that are always online. Mobile devices can be on or off. When mobile devices want to send queries, instead of randomly choosing a mobile device on their own, all the mobile devices are randomly connected to brokers. Each broker is connected randomly to K unique devices. And when they have a query, they send this query to the brokers that they are connected to. Each device may be connected to more than one broker. Each of the brokers will then propagate that query to other nodes, collect their responses, aggregate them, and send kind of the majority vote decision to the nodes that are connected to them. And so because each mobile node is connected to multiple brokers, again, there is a consensus process. Eventually, the information spreads across the collection of validating nodes in a shard. But all of this is happening in a way that's intermediated by these brokers. So that's kind of the nature of the solution. Would have to be two-tier. We're going to have to introduce these broker nodes. The challenge it poses is that now, from a security perspective, you have to worry about the Byzantine fault tolerance with respect to Byzantine behavior, both at the mobile devices and at the brokers. So you have two classes of devices that you have to worry about their capabilities. And one possibility also is that they might collude with each other. So if you built a protocol where any node could connect to any broker, they may select these brokers in such a way to make the system insecure. And so one contribution of this work is kind of to use a distributed random matching scheme that connects each broker to K random mobile devices in such a way, and uses these random beacons that it can be verified that there's no way for a mobile device to arbitrarily choose whom to connect to. They have to kind of follow the rules of the system, and this prevents kind of collusion in the matching. And so the bulk of the technical work in this paper, and again, there's a lot of detail analysis there for the safety, but the crux of it is that we want to show that even with some subset of the broker nodes being Byzantine and some subset of the mobile nodes behaving in a Byzantine manner, that we still get safety of the protocol, that nothing bad can happen, essentially, right? And so, and to derive then conditions under which that can be, that statement holds, that the system is safe. Like what fraction of your brokers, what fraction of your mobile nodes can be Byzantine. And so there's some assumptions we make in the paper about the behavior of both the mobile nodes and Byzantine nodes. They're here on the screen. I won't belabor the points, but essentially the brokers, even if they're Byzantine, are not allowed to forge information because they don't have the keys that correspond to correct mobile nodes. So they can't pretend to be a correct mobile node because they don't have the keys corresponding to the mobile nodes. But what they can do is they can censor information from mobile nodes that they're talking to if they're Byzantine. And they may drop some of the information they've heard so as to try and manipulate the consensus perhaps towards the bad to agreeing that an invalid transaction is valid. And so the crux of the analysis is to show that despite some amount of Byzantine behavior, both at the nodes and at the brokers, you're still able to guarantee that the consensus happens to the correct valid solutions. And what we find in our analysis is that this type of protocol, typically when you specify BFT consensus protocols, there's just a threshold, typically something like, at most 1/3 of the nodes can be faulty. And if so long as that statement holds, the system is guaranteed to be safe, right? It's going to arrive at the correct conclusion in the consensus process. Here, because we have the sort of two dimensions of the number of brokers that can behave in a Byzantine manner and the number of nodes that can behave in a Byzantine manner, we actually show that you end up, in fact, at a two-dimensional safety region. So there's certain combinations of nodes being Byzantine and nodes and brokers being Byzantine that you can tolerate. Here it's shown in the yellow area. And how large that area or that region of safety is depends on parameters like how many nodes there are in the system, how many brokers there are in the system, how many mobile nodes does each broker connect to. So for example, in the bottom right, we have, in this example, 170 brokers, each of which is connecting to 35 mobile nodes. And I think that there's also a total population of mobile nodes, which I've left out of the slide here. But under certain parameters, you can see that the safety region is a little bit bigger when you have more brokers and you have more connectivity between the brokers and mobile nodes. And the larger that safety area, the more faults you can kind of tolerate on both the broker side and the node side. And what's interesting here is that the threshold, assuming, for example, there are no Byzantine brokers, and you see kind of like what is the threshold that it's converging to for the nodes, and in the other direction, where if none of the nodes are behaving in a Byzantine manner, what is the threshold that you can satisfy for the broker Byzantine? They're not necessarily symmetric. So this region is not a symmetric region. There is differences in the impact that a Byzantine broker can have versus the impact that a Byzantine node can have in the system. The other things in this paper that are actually generalizable to other consensus protocols is kind of a framework to analyze the throughput and latency of a blockchain protocol, particularly one of this class of gossip-based consensus, but I believe it's actually applicable to other protocols as well, is essentially to look at it, even though it's a distributed protocol, it has a set of stages of computation and communication that are going to happen. Here's kind of the set of stages in this particular Blizzard protocol laid out. And then when you want to understand the throughput of the system, really what you have to do is to understand, like, is this particular step, 1 or 2 or 3 or 4, is this step the bottleneck step? Which step takes the most time to finish its computation or the most time to transfer the data? When you identify that bottleneck, you can essentially focus your attention on how long that time is, and 1 over that time is going to give you the throughput of the protocol. Because that bottleneck time determines, like, even if you have pipeline information going through this, it is that bottleneck that's really determining your throughput. When it comes to latency, it's in fact the sum of the times of all these blocks, because whatever new transaction comes in, it has to go through every one of these blocks. And so you're able to kind of use this system view of a protocol to analyze both the throughput and the latency. And we did this specifically for Blizzard, but there's a methodology in the paper for doing this that you can apply potentially to other protocols as well. And so using that methodology, we were able to characterize this protocol and identify, that the bottleneck most often happens to be block number 4 here, which is a computation block that would happen on a mobile device. And by benchmarking that computation on a mobile device or an equivalent desktop, with similar computation or worse computation capabilities, we're able to say it's going to take roughly 100 microseconds. And that implies something like 10,000 transactions per second per shard that you would have in the system. And you can then also characterize the energy expenditure associated with processing one transaction. Turns out, again, by analyzing these blocks, their energy expense, you can profile the protocol's energy usage, which for IoT is often important. If you want to involve these devices in the consensus protocol, how much energy are they consuming can also be analyzed this way. And then finally, we're able to kind of characterize the end-to-end latency of Blizzard using this process as well. And so, so the paper makes a lot of contributions, I think, both in terms of just the ideas of extending consensus to offline nodes by using brokers carefully, analyzing the safety of that system, but then also presenting a methodology for analyzing the performance, both throughput and latency and energy expenditure of the protocol. So this switching to a different contribution of ours that focuses on a little bit more at the application layer, not the consensus, but still very much decentralized IoT as the focus, is that IoT systems, one of the common mode of communication in them is pub/sub, right? We use things like MQTT, and it allows us to connect large numbers of sensors and actuators together. Sensors can publish data, dashboards and mobile devices, and even actuators can subscribe to information coming in that tells them what to do or shows what's the condition of your IoT system or the data feeds that are coming in from your IoT devices. But these typical MQTT type of pub/sub systems are centralized. There's a single point of failure. And more importantly, not just a single point of failure, it's a single point of trust. Like everybody has to trust whoever's running that broker to not manipulate the data, to not withhold data, to not censor the data, to not present different versions of the data to different entities in a decentralized multi-stakeholder type of application. So how do we address that has been kind of the focus of this work. And in fact, Dr. Gauri, who's at QUT, led this work when he was at USC. So Trinity, in comparison to the prior work on pub/sub, is decentralized and is also providing Byzantine fault tolerance, which sort of traditional centralized pub/sub protocols that we came across don't. They really focus on crash tolerance, but they don't really worry about Byzantine fault tolerance. And that kind of goes hand in hand with the centralized assumption. Like if I own the machine, I'm not worried about the machine behaving badly because I own it, right? It's a security issue at most, but I'm not really worried about Byzantine behavior on that single node. When I have multiple nodes that are participating in a decentralized fashion, I could be worried about, should I trust them? What if they behave maliciously? And that's where this kind of Byzantine fault tolerance lens comes into a decentralized system. So Trinity is a decentralized pub/sub protocol with a blockchain-based immutability guarantee if you want to persist the information. It allows distributed brokers to be hosted on-premise or cloud by different organizations and stakeholders. The biggest guarantee you get out of using Trinity is that everyone is going to see the same stream of data in the same order. And the way it does this is it basically integrates a standard pub/sub broker, for example, an MQTT broker, with a BFT consensus protocol, and essentially creates a bridge between the two, right? And so this is what the bridge might look like. So you've got different brokers in different administrative domains. So if imagine this is sort of broker for domain 1, here's a broker for domain 2, and so on. So these could just be traditional MQTT brokers, and every one of them is connected to the consensus layer. And so every message that is being published by the publishers within the first broker's domain is going to enter into the consensus layer. And only when it's kind of verified and consensus has been achieved on it will other brokers accept it and then forward it to their entities, right? And we're able to show that the system satisfies correctness and safety and liveness, and under essentially an assumption that no more than a third of the domains that the brokers correspond to are faulty, have Byzantine faults. And so long as you kind of restrict the number of those, you're able to kind of benefit from it. The system that is bridging the broker and the consensus, like the bridging itself is new, but both the consensus layer and the brokers can be off-the-shelf existing solutions. So you can take any existing BFT consensus protocol, you can take any existing centralized pub/sub protocol and essentially create this bridge that Trinity kind of represents. And the analysis in the paper kind of shows that if you do this composition the right way, you're able to kind of guarantee the fact that whatever sequence of messages one correct node sees in the entire system is exactly the same sequence of messages that some other correct node in the system would see. And we've actually built it out and implemented it using Tendermint. And in fact, to show that the system scales to other domains, have also done it with Hyperledger Fabric. We use an MQTT broker. I believe this was the Mosquito broker, and tested it on Raspberry Pi testbed, so it's actually relatively lightweight, thanks to the Tendermint consensus being lightweight to begin with. We're able to kind of validate the system and show how it scales. For example, as you change the number of brokers, you do get a higher delay because now you have a lot more brokers that need to participate in that consensus process. It's going to increase the end-to-end latency. But for certain applications where you're able to tolerate, a few seconds of latency, but you want that the benefit of the security guarantee that you're getting from it, the trust guarantee that you're getting from it, this would be, more than applicable. So I'm going to switch gears to some case studies that now look at the question of buying and selling IoT data and where blockchain can be relevant to those. And again, it's this question of trust boundaries, but now the question is the trust boundary between where data is being produced and where data is being consumed, right? In a typical, what I would call IoT 1.0 solution, it's just one organization that has deployed, or one entity that's deployed the IoT data sensor and is consuming the feed from that sensor, right? In fact, most IoT deployments look like that today. In fact, one of the reasons IoT is not able to scale is the silo that we're kind of forced into. And so if you want to break out of that silo, if you want seamless movement, frictionless movement of data across organizational boundaries, economic boundaries, trust boundaries, we're going to have to find a way to make this economically worthwhile in the interest of all parties concerned, right? The data providers should be able to earn enough from their data to make it worthwhile to share that data. And on the other side, data consumers should be able to pay enough, should be able to guarantee that the data that they get is the data that they're paying for. And that allowing that to happen in as frictionless a manner will allow these IoT systems to scale. And the point is that in some cases, these organizations may not have a prior relationship with each other. So it may not be a matter of sitting at a table and negotiating a contract and agreeing to pay over a course of months. It may be very ephemeral data. So you want to do something that's very lightweight, that's very easy to set up and make happen on the fly, rather than requiring kind of a long-term commitment and a lot of manual executing of contracts. And this is where smart contracts, for example, can come in and blockchain can come in. So just as a simple example, perhaps it's a trivial example, but just to kind of motivate this type of thing, you have a food truck vendor showing up in a new city. She wants to find out across the city in different locations, where are there most pedestrians, so that she could have an advantage in finding the best site to park this food truck and to maximize their revenue. So an IoT vendor in the area may have information about pedestrian traffic that they'd be willing to provide to such a street vendor, and maybe it's based on camera feeds or whatever is the source of it. And you want kind of to be able to gather that information from the nearby sensors and pay for it on the fly, right? So there's an incentive for that data provider to share that information and make it seamless to be able to connect and pay for it. So one of our contributions is proposing a hybrid protocol that takes the client-server model of the traditional internet protocols. So you've got the buyer of data as a client, and you've got the seller of the data as a server. And there's kind of the data channel is a very traditional TCP, with TLS for encryption data channel. But then in parallel to this data channel, we also want to set up a payment channel and a records channel. The payment channel is to actually make the payments, and the record channel is to store information about and log information about a transaction. And in the data channel, besides actually getting the data, you're also exchanging relevant other transactional elements, like what type of data do you have on offer? I want to buy this particular data. Getting an acknowledgement that that data was received, getting an invoice for the data that you've consumed, and making a payment, sending an acknowledgement that the payment's been made, etc. So there's all kinds of other transactional data that might need to be sent. And sort of SDPP as a protocol gives you that ability to kind of wrap all of this into something that two endpoints can simply plug into, and makes each of these elements kind of modular in that, for example, your payment could be in cryptocurrency, or it could be a traditional payment rail. Your records could be a traditional database, or it could be a distributed ledger. So it doesn't have to be necessarily blockchain that's used here. If, the sort of state of the art isn't quite there yet. But as these things become much more prevalent, other forms of digital payment, micropayment become available on blockchain. SDPP can kind of naturally scale to handle those. It's in a way kind of an architecture for marrying, the old-fashioned internet protocols with the new capabilities that blockchain systems have to offer. So one of the elements of SDPP is a parameter we call the granularity parameter, which is essentially each time you make a payment, how many units of data did you get from a server? And so if you have kind of this parameter to be quite large, then things are kind of moving faster because you pay once every, let's say, I don't know, 1,000 pieces of data. The data can keep flowing. You just pay once in a while, right? And there's less kind of friction in a way, but you also have more potential for loss to either side. So it could be that you paid in advance and the server stops sending you the data. So you're out like 1,000 units of data that you paid for and the server's refusing to provide it. Or the server's sending you the data and you're not paying it and you just move away if you set it up in the other way. So there's sort of this buyer-seller dilemma that's often present in exchanging digital goods and paying for them, that in this case we address with this K parameter, where if K is large, you're exposed to more risk with respect to this issue, but as it gets larger, you're also more efficient. So you're kind of trading off efficiency or latency of your system with risk. And I'll skip this, but essentially we're able to evaluate and show that as you have more essentially evaluate the statement about performance essentially getting worse as you reduce K, but in exchange for greater guarantees of both parties being paid. I think I'm going to actually skip this video and come back to it if we have a little bit of time at the end. We have a work that kind of took this idea of SDPP and then applied it to the context of vehicle-to-vehicle information transfer and payment, but I'll maybe come back to this if we have time, or at least maybe leave a link to it that people can go look at. It's on YouTube, this video. So the problem that I identified with the granularity isn't quite satisfactorily addressed there, because you've got this parameter and you've got some risk, and it would be nice as if there was a system that kind of reduced the risk to zero. So we have a work from 2019 that addresses this fundamental buyer and seller's dilemma, right? So it's a very fundamental problem in trading digital goods. If, let's say, I said I wanted to buy a PDF file from you, we could do it one of two ways, right? We don't know each other. We're on either ends of the planet, perhaps, and over the internet, complete strangers to each other. And you say, hey, I'll send you this PDF and you can just pay me later. So you email me the PDF and I can just disappear at that point. I don't have to pay you, right? Because I already got the PDF. And the other direction, perhaps the next time you get wiser and you say, hey, you got to pay me before I send you the PDF, and someone pays you, and then you walk away because you realize you don't actually have to part with any information once you got paid. So you've got the sort of who goes first and how do you get paid as a kind of core challenge there. And it's a known problem in kind of the domain of digital commerce, and it had always been assumed that you needed to have a third party to guarantee honesty, that you would need a third party that you can go to as a reliable broker in case of some problem with delivery or with payments. This is why we have credit cards. This is why, when various shops actually use Amazon as their fulfillment platform, we're also using Amazon as our trusted third party, that if we have any problems with delivery, we can complain to Amazon and get a refund. They can, because they have a relationship with these other vendors, they can take the money back from them, etc. So without a trusted third party, what can you do? We present a solution in this work which uses what we call a double deposit escrow. And the idea is kind of similar to what you might have experienced anytime you've stayed at a hotel or rented a car, where they ask you to put in a deposit before you can take out the car or stay there. And they're really doing that because they're worried you'll leave without paying, right? But here you have two parties that are concerned about either's behavior. So you don't just need a deposit from the buyer, you also need a deposit from the seller. I'm oversimplifying it. There's a little bit more to the protocol, as you'll see. There's a slide here. And again, not as much detail as perhaps I would love to get into, but the crux of it is both the buyer and seller must put in a deposit. Then we go through the protocol to exchange the data for the buyer to verify that they got what they were supposed to, and everything goes well. They simply acknowledge that they got what they were supposed to, The payment goes through to the seller, the deposits get returned to both the buyer and seller. If the buyer doesn't get what they were promised, it has a way to show the smart contract that the hash of what it got doesn't really match these promised known digital good. And in that case, you can potentially slash just the seller's deposit. So the seller would be very wary of cheating the buyer in this case, given the seller has some asymmetric advantage. And so there's a bit of a protocol that looks at the hashes associated with the digital good to register the complaint, etc. But what's really nice with this protocol is that you can actually analyze it game theoretically. We use a game tree analysis and actually show that the subgame perfect Nash equilibrium of this game is achieved by a strategy profile where both the buyer and seller essentially choose not to cheat either party, and they both behave honestly. That in fact, that is for rational actors the right thing to do. Now, the thing is, in the real world, the people that are engaged in an exchange are not always rational actors. If one of them is malicious, if it doesn't cost them too much, they might be malicious just to hurt the opponent, not necessarily in their own self-interest, but because there's some other interest that they value the other party getting hurt. But in this protocol, you can also show that by essentially increasing the value of the escrow amounts, you also deter this type of malicious behavior. So if you can figure out what is the point at which somebody would not be malicious, then you can also raise the cost to malicious behavior. Now that comes itself at some cost, because the higher the escrow amounts are, the more somebody has to be willing to put up front just to do this exchange. And the ratio of the escrow amount to the actual good being exchanged can itself be a deterrent in terms of people willing to participate in the trade. But it's kind of a nice solution to a problem that has been there for a long time, does not require a third party. It's just using a smart contract as a solution. And again, there's kind of a nice analytical way of proving mathematically that rational actors would not cheat, and even malicious actors would be dissuaded for a sufficiently high setting of the escrow. The last one I want to mention is a work that we've done on decentralized ratings for marketplaces. Particularly data marketplaces are a growing area of interest in IoT. And the problem really all online marketplaces have with ratings. So what's the idea is that you want the buyer to know what is the quality of this product that they're paying for. It could be a data product, could be a digital good, could be something else that they're buying on an online marketplace. And what you're always worried about is there may be some manipulation of that rating system. Perhaps the sellers are paying reviewers to come in and give them good ratings. Perhaps the platform is censoring reviews in some way to manipulate buyers, in a way that it benefits the platform and not necessarily the buyer, perhaps even not necessarily the seller. So, and particularly when you realize that in a digital environment, your sellers can even launch Sybil attacks. They can impersonate many different reviewers and come in and post a bunch of reviews. It really is a kind of fundamental problem with trustworthy ratings. And so our goal here was to design a decentralized crypto economic system that would help to ensure credible ratings. And this work was in the context of decentralized data marketplaces. I'll just mention briefly that we've written this kind of overview paper identifying a number of aspects of data marketplaces that can be decentralized. This particular work is just looking at the ratings component. So having a random selection of anonymous reviewers for each product is important. And this goes back to preventing collusion between the sellers and the reviewers. And a similar type of decentralized matching that we showed earlier in the context of Blizzard can be used here as well. And then the other is the use of test products and incentives to encourage reviewers to actually do the review. And I'll show in a bit. Essentially, we create a game matrix, and we consider the incentives that reviewers might have to actually do an honest review and present the ratings versus just kind of, cheat and be lazy and not actually do the work of reviewing the product and simply, give a rating, good or bad, without thinking about it. And this also has been a big known problem in data curation systems. There's a class of solutions proposed for blockchain called TCR, token curated registries. And prior analyses on TCR shows that the lack of incentive for participants to vote correctly can mean that the system that you've created actually can end up with really bad solutions where they instead of curating good quality products, they end up curating bad quality products. And the reason is that they kind of lack any notion of ground truth. And so the system we are describing here, there's a notion of test products that you know the ground truth as to what the correct answer should be, and you periodically test these reviewers to keep them on their toes, randomly test them with these test products, and use their review for the test products for which you know the ground truth, is it a good product or a bad product, to be able to, and to give them some incentives based on those test products to essentially incentivize them to behave honestly. And again, it's designed to be easy to implement in a decentralized smart contract setting. It's kind of an architecture for decentralized reviews in the paper. I won't go through all of the details, but again, the crux of it is choose a random reviewer, periodically test them with these test products, and other times give them the product they're supposed to review, collect their ratings. If it's a test product, you know the correct answer, and you can penalize them for giving the wrong answer or reward them for giving the right answer. And for the normal products, which are not test products, you could just use the majority voting, right? TCRs, which were proposed earlier, did not have the concept of a test product. They only use majority voting, and that has an equilibrium selection problem in it, which can result in bad quality solutions. So I mentioned that you can take that problem of our reviewers actually going to be on their toes and do a good job of doing an honest review, and we're able to kind of analyze what that game matrix payoff would look like. And one of the parameters, or two of the parameters in the system, essentially have to do with the rewards that you're giving for test products and regular products. And we're able to show essentially that by choosing that incentive sufficiently high, you're able to incentivize reviewers to actually do good quality reviews for this for the system. And as you might expect, almost intuitively, the more lazy the reviewers are that you have in your pool, or harder the reviews are to do, the more your incentive has to be to actually convince them to do the right work. And also, the more frequently test products are provided, the less reward you have to give per test. But essentially, it's saying that there's kind of the way the ratios work out, essentially there is a certain amount of incentive you're going to have to put for the system to operate, right? And so long as the products you're selling on this marketplace are sufficiently high that these incentives are worth it, and not causing too much of an overhead, you can actually have a good quality data marketplace with reliable reviews. So at the end of the day, it kind of boils down a little bit to what incentives do your reviewers need, and what fraction of the total cost of the data products being sold is that incentive. And if it's too high, let's say the ratio of the incentive needed to the actual data product cost is too high, then it might be too much overhead for someone to implement. And so this is likely to work better for a system with, let's say, high quality, more expensive data to some extent, or that in particular, if the data is hard to review, it has to be really worth it for the system. So I'll really just stop there because I want to take some questions, if there are any. Just to say that this is an exciting time to be working at this intersection, a lot of interesting challenges. I've touched upon some of them. If you're interested to learn more about our ongoing work, please check out anrg.usc.edu, and you can find your way to our blockchain research page. Thanks.
Thank you so much, Professor Krishnamachari, for your wonderful talk. It was very insightful. So any questions?
Yeah, I'll jump in if I can.
Sure.
Yes, please, Kevin.
I'll turn my camera on if
yep, can see you.
It works. There we go. All right. Well, thank you very much for that talk. A lot of interesting takeaways, a lot of interesting things to consider. The 8 fallacies of distributed computing were great. You can sort of, as you live your life, you sort of see, oh yes, there's that.
Yep.
So
checking them off, yeah.
It's interesting to think of proof of work as a civil attack deterrent. You sort of think of it as being proof of work, just that somebody's done some work. But then again, you really want to make sure that you're not be able to deploy massive amounts of computers en masse. And it's interesting to think about it in that context. Maybe a philosophical question more than a technical one. A lot of projects, they start off very idealistic and well-meaning, and they have all these sort of great objectives. But then someday they get put out into the real world. And even if they're delivering code updates, nobody has time to do a full analysis on updates of every code base that gets pushed. So, you imagine that if there is a system that's seeing a lot of transactions on, great economies going through it, Mt. Gox might be a good example. Eventually it becomes a target. And even if you can withstand all the technical attacks, there's still going to be this sort of political and economic forces internally that are going to be trying to push it in a certain direction for the sake of someone's gain. Maybe just on a high level, do you have any thoughts on preventing these systems from getting corrupted over time as additional code pushes go forth?
Yeah, I mean, I think you're highlighting one of the biggest issues in this space, right? A lot of the claims about immutability, transparency, security are theoretical statements, right? I'm happy to make them in my lab and in my papers. Like if you implemented the perfect ideal version of the system, you have all these guarantees. But what gets deployed in the real world is real software, and the real software has bugs, has all kinds of issues. So that aspect of vulnerabilities in the code or these updates not doing quite what they're supposed to do and not figuring this out until someone's attacked it, right? And of course, that's the world of the arms race of cybersecurity and vulnerabilities we've lived with even in the centralized cloud-based infrastructure world. But it's worse now in a way because now we're becoming maybe more reliant on the trust that these systems are supposed to provide, and they can attract malicious actors. I actually don't have a good answer to that question myself. I think, again, people are looking at various things from more secure programming environments to even making certain aspects of the code that's running, encrypted, but then you lose some of the transparencies, so like what would that look like? So, and I think you're asking a very good, deep, important question. And to date, the record of the number of hacks and the amount of damage that's done on blockchain systems isn't encouraging, right? There's a lot of that. There's a different aspect to your question, though, which is actors who have an incentive to steer even a decentralized platform in a way that may be contrary to the original spirit or the claims of the project. And that's almost like a meta question about governance, perhaps, right? What measures were put in place here to prevent that sort of thing from happening? And governance is hard. Decentralized governance is very hard, right? And we've not really solved it in the real world, even non-technological world. With our governance systems around the world, always subject to various shocks. And it is very much a social and a political and an economic, hairball that has to be thought through and untangled. And it's not a technological issue alone. That governance thing often, that you've set up a platform, what were the founding principles, what was the constitution? There have been efforts to kind of decentralize the process of voting for what the constitution of a particular blockchain platform is going to be. But who got to vote at that time? What was the composition of that? Like, were they agreeing on the right decisions at that time? How easy is it for somebody to split off and start their own chain and fork a different version of it? Like, all of these things are quite unclear and fragmented and are likely to be there for a long time, if not ever.
Yeah, absolutely.
So I don't have good answers, but I think there's a lot of but there's still a lot of meat there for research too at the same time to kind of poke at pieces of this and say, maybe I can't solve all of it, but here's one, thing that I can systematically explore and say something about, right? I think that's often the nature of the game, is to kind of pick apart at something there we can say something about, maybe not. Yeah.
Yeah, and I appreciate you taking a very nebulous question and running with it, because it's more just about gathering your thoughts on it.
Yeah.
It's a problem that I don't think there is a straightforward solution to. But it's interesting to think about and sort of I guess contemplate how various factors interact with that problem.
But I think it's also a question that points to the need for interdisciplinary research that goes outside engineering, because I think some of that, the second part with the governance and so on, I think does cross disciplinary boundaries, and we should be talking to people that have more understanding of governance from political and legal perspectives, etc.
Absolutely. Well, thanks for your thoughts.
Great question.
Hi, Professor. I have a quick question. I'm happy to see some of the work again after some time. And I haven't followed Blizzard that much while I was there. And it seems like there is some some comparison between Blizzard broker and Trinity broker. So could you please explain if there are any similarities between the two? Because the analysis that you showed with the graph that's showing how the system would behave if there are more.
The correctness of both the brokers' devices. That's interesting. I guess I see this different for the following reason. So in Blizzard, both layers. So the first of all, what's common? So what's common to both Blizzard and Trinity is that there is a two-tier thing. There's consensus nodes and there's sort of end device, like broker nodes at each node, each organization and their nodes, the device nodes. And here we've got the online brokers and we've got the device nodes, right? And so it has this two-tier bipartite graph structure. That's similar. But the difference, I think, is quite fundamental between the two, is that Blizzard is a consensus protocol at the lowest layer. So what all of them need to collaborate on, both the end devices and the brokers, they all need to collaborate on like everyone in the system has to collaborate on the consensus or to validate a transaction. So everybody's trying to do the same thing, right? Whereas in the Trinity system, your end devices are either publishers or subscribers. And each publisher is only publishing the messages that they're publishing, and the subscribers are only subscribing to whatever they care about. There's not this sort of universality, and they're not working hand in hand with every broker to achieve a common objective for the whole system. And I think because of that subtle difference, I'm not sure if the Byzantine behavior analysis we do for Blizzard, or like that style of analysis, is also applicable to Trinity. Because Trinity, I think it's much more about the Byzantine behavior of the brokers. Because not all of, you can't put all the publishers in one bucket, like on one axis, and say, what are they all doing? Because they belong to completely different, orgs, and they're not all doing the same thing at the same time.
But one of the strong assumptions in Trinity is that the domain has to be honest, meaning that the publisher and the broker within the domain are honest.
Same domain.
So the publishers just publishes to broker and assumes that that everything happened correctly. But from the subscriber's point of view, there is no clarity on whether the things happen correctly at the upper layers. So the publisher needs to also request data from other brokers in the Trinity network to ensure that the right consensus happened and all the brokers, have.
Yeah, so you could distrust your own broker, actually, right? So we do have that possibility. Yeah.
I think if you bring that in, then I think, Then
well, so one way to connect the two is that in Blizzard, you do require each mobile device to connect to multiple brokers and each broker to connect to multiple devices.
Yeah.
And so having that kind of web, of connections across the client layer and the broker layer in Trinity could be beneficial. I think
Yeah, actually, I'm writing that up for the journal version of Trinity. And I think I'm saying that you have to connect to multiple brokers if you want
to have that. Yeah. That's a reasonable point. I see that. Yeah.
Thanks, Professor. Yeah.
Sure.
Thank you. Any other questions? No, I think that's all for today. And
all right. I'm going to do one shameless plug, Shantanu, since I have an audience here. We have a couple of books coming out. Both the one is the second edition of a book that's already been out since 2019 on blockchain and supply chain. This is with co-authors who work in supply chain. And the other is a handbook on blockchain, to which many of you have contributed chapters. So thank you for that. And this is going to come out in September 2022.
Yeah, thanks for this information. And we are really looking forward to that.
Great. Thanks so much for hosting me.
Thank you so much once again, Professor Krishnamachari, for your talk today. And we hope that at some point we maybe host you very near soon here at QUT.
Sounds great.
Okay, thank you.
Bye.
Yeah, thank you all. Bye.
Bye.